Hello again. Now that we finished the modeling and also the boundary and expectations, I'm gonna go and run the simulation and check the results. Um, I already ran the simulation, so it's pretty fast. So basically you click on that and then you analyze everything. The first thing you want to do is you want to go right click on the results and go on the solution data. And on the solution data, one of the things that you want to check first is the profile. Actually, if you go on the profile, next one is actually instead of the profile you can go to the coverage as well, but in the profile you can see that how much memory has been used. In this case 700 meg of memory has been used. It's good to know that 400 megabyte of the memory was just for the tetrahedrals that been used for the meshing. We have 120,000 tetrahedrals here, which is very high number of meshing sections. On the coverage, if you go on the plot, you can see that in order to fix a problem, it was increasing the number of tetrahedrals to basically have a more accurate result. You can, as always, check the energy error, which is pretty low, and also the total energy here that is about 0.088 joule. On the force section that we just defined, you can see the magnitude of force that is applied into armature, and that force in Newton is 196.51. You can see where are the other two axes. Honestly, for X and Y axis we shouldn't have that much of a Newton force, which we don't, and the main force is in the Z axis, which we were expecting that it's going to basically drag it down because of the inductance. Sorry, because of the magnetic field, and the magnet basically makes the steel a magnet, and then it will drag it down. You can also check out the matrix here, and you can see that for the current here we have for the current one we have inductance value in millihenry, and there is no need to select the post processes because we haven't defined any terms. It's just one turn, so it should be the same when you click it. And as you can see, we have for the current one, which is the coil one, we have let's make it on micro or nano maybe. Yeah, we have 528 nanohenry of inductance. That's the inductance of the coil. Okay. Now what we want to do is we want to set up a parametric analysis in order to get a better feeling about the force and the gap and inductance. So to do that, we want to first know that the inputs here is going to be the ampere turns, or the current that we are applying for the coil, and also the gap value. So I want to see what will happen if you change these two parameters. The output here are the armature force and also the coil inductance. Okay, one thing you want to do is you want to go on results under the model the Maxwell 3D, and you want now to create output variables. So you select on output variables, and now we have this chance to select what kind of variables we want to show and have it as an output. So in the parameters, we select first the force 1 that we define, and in the category of force we want to go and find the quantity F max, and then we want to insert that expression there. Okay, and after we did that, we want to have nothing, no mathematics is going to be done on that, so simply we just say add. oh sorry, you have to put a name for that. So let's say the magnitude of force. Okay, so that would be the magnitude of force. I'm adding that, and also I want to have x, force x. I call it F, probably x, and then I want to have F force in y direction, so I want to call it F underline y, and also I want to have F in the z direction, which is the main one, and I want to call this one F underline z. Okay, and that would be all added. Also we can add some matrices here that basically this is the coupling coefficient here, and so in this category we are not looking for the coupling because we have only one inductance, I mean one coil, so there is no coupling. So we go for L, inductance, and this is L current 1, which is L11, and now we can just select this expression and we can call it the inductance or induct, and press add. So now we should have induct value over here. There, it's all added, and now I think we are done with this defining of the output variables. Now we want to have also a sweep where we can sweep the variables and check out the results. So to do that, you go to optometrist here and you right click on that and add a sweep, a parametric sweep. And over here we want to make sure that we are adding a gap sweep, and the gap sweep is going to be a linear sweep, and it's going to start from 0 inch, and it's going to start from 0 inch, and it's going to stop on 0.006, and the step values are going to be 0, 0, 0.5. Okay, so that will give us a lot of sweep here. I'm gonna add that so I can have it there. Also, since we are here, we can have another sweep. We can have the sweep for the input current, and the input current we can actually put -1 here for the amp, so it's pretty small. So single at -1. Now we can have other values for the amp as well. So we can have, let's say 330 amp. We can have, for the single values of course, we can have 661, and also we can have 992 or 95 amp, and now we can say that we are good with this variable sweeps that we defined. We have gap definition linear, we have amp input current definition the single values, basically 4 values here, and now we can press OK for that. So now we define our sweep. So on the calculation tab also we want to add some parameters. So to do that, you select on setup calculation, and under the parameter of force 1 we can select output variables as we defined, and we can actually select oh, you cannot select all of them at once. So you basically select one by one and put them here. So you want to have these different values of forces here, and these output variables are going to be calculated each time that the sweep is happening. Same way, you want to also have the matrix 1, and you want to have the output variables for the matrix 1, which is just the inductance. Also you want to add that as well. and that's done. On the option tab though, you want to make sure that the, the equivalent mesh is also checked. That will help us to have a faster simulation, which is good. Now that we have finished that, we are good to run our first parametric sweep. To start that, you just need to open up this Optometrics, and over here you right click on that and say analyze. Okay, I'm gonna do that and it will take some time. After the analysis is finished, I will record again and talk to you about. Hello YouTube. So I just finished the simulation. It took actually a long time, and now that the simulation result is finished, we want to go and check out the parametric setups. The same way that we do for the analysis, we can also right click on the parametric setup and go to the view analysis results. And as you can see here, we have the results, and based on what you want to see on the X and Y, you can basically choose different things. So I'm going to go, for example, for the Z force, and you can see that the minus magnitude is increasing, meaning that the forces, the absolute value of the force is increasing if I increase the amp per turn, which kind of makes sense. And you can also change the X variable. Instead of amp turn, you can make it gap, and you can see for the different values of the gap, you have different. So let's say for the different value of the gap, we want to see what kind of a current we want to apply. Let's say we are putting the current of 995, and then you can see that for that, when you change the gap, you get actually less and less force when you have a bigger gap, which makes sense again as well. That is the quick view of the output variables. If you want a table, you can see them on the table and follow the numbers there if it's easy for you to do that. That is also an option. So I'm going to close that. Of course, you can export it to CSV, and you can use it later on in MATLAB or any other software that you're using to post-process the simulation results. One other thing that you want to do is I want to show you how to create the plots on top of each other. So one thing you can do is you can go to the Maxwell 3D, and under the results, you can go and find the create magnetostatic report, of course, and then you want to have a rectangular plot. Of course, here we have a stacked plot, we have data table, we have 3D rectangular plot, and we have rectangular contour. As the name actually express, these are different ways to represent the same data. So don't be like all like bewildered at what's going on here. The data is data, the table, basically it's kind of useful when you're looking at the small number of changes, but if you have a lot of plots and stuff, the data cannot help you, the table cannot help you to figure out the trends of the change. The 3D rectangular plot is going to basically put a 3D image of basically more than two variables. If you have changed more than two variables, when you go with the rectangle plot with not 3D in a 2D, it will basically add different number of plots in different colors. So let's go for that one, and I will show you what I mean exactly by that. So when you select that, you want to check that your solution is the last adaptive solution, and also for the parameters, which parameters you want to choose. Let's go for the force and see what are the force in the different for example, current. So the primary sweep here is going to be the current, not the gap. You can actually go for the gap. Actually, I will select the gap here to see that. So when you select the primary sweep to gap, it actually tells you that the X is going to be gap. You can change it if you don't like the default, but you know the default is right, and I'm going to go with the gap. So the Y is going to the force magnitude, which is not a bad thing actually. This fine. And so we can go with the force magnitude here, and it doesn't make any sense if I say magnitude of the force magnitude, because it's already magnitude. But you can actually change it to dB which is not a good thing for force, but any other stuff that you want to do. ABS is a good thing because you want the absolute value, so that's one way to do that. Although it is an absolute value, what I'm talking about, because it's not even the should be the absolute value. Okay. Once we are here, I can tell you that you can also do some simple math here. You can add more math here by clicking on that, but if you are going to do some simple math, for example, this plus this, oh, you have to actually type it down. That's the problem. So if, for example, you want to add this force with the force that you have on the y direction, you can just say add, and then it will do that for you. And as you can see, when the color is blue, it means that it's valid, so it will do that for you. So let's go with the force max, and I'm going to have that versus the gap switch. And the only thing I want to do is just to say new report, and I close that. And you can see that for different currents here, I'm getting the different force. So for a -1 current, basically you get nothing. So it's not even showing here. It's pretty small. If you double click on that and you go and say I'm gonna make it a logarithmic, then you can basically see all the different colors, I mean all the different ranges. So even for the forces that you can have for -1, you can still see the force here. But if you don't like to see the force in a logarithmic way, you can we can actually come back to the same linear range by double clicking on the numbers, any numbers, and just select linear. Look, I'm actually under the scaling tab. Okay, so press OK on that, and basically you are not seeing the very small one, which is the red one, which corresponds to input current of -1 amp. But for the larger input currents, of course, you can see the magnitude of the force. Of course, when you increase the gap value, the magnitude of the force will decrease as well. One other thing that you can actually do is you can go do the same thing by right-click on results and go here on the create magnetostatic report, rectangular plot, and also you can here have the same plot of the magnitude, but on the based on amperturn, and you can here say new report, and then you can see for the new report for all different values for the gap, you can see how the force will change when you basically increase the current. So you have two variables, and there's two ways to basically follow the result of that variables. Okay, so far we were inside the Ansys Maxwell model. Now one other thing that we can do is basically we can extract the parameters, the analysis parameters, and then we can use that in the other simulator. So at this part, I'm going to basically end this simulation, end this tutorial, and go with an extra part that is going to be dedicated to the Simplorer part of the design. And in the Simplorer part, I'm going to import this design, and I will tell you how to import that and also analyze it, a quick analysis there. It would be a time transient analysis of the magnetostatic analysis that we have here, which you might say that how we can have magnetostatic and over there we can have time results, but you can see that it's all possible and there is no problem, and the results is actually accurate. So we will see there that how the simulation results are going to work there, and we can discuss more in the Simplorer side in the next tutorial. Please let me know if you have any comments, if you have any questions, and leave it there below. I will answer that questions. And you can also subscribe to the channel, as you can see below. And I'm trying to have 1 to 2 videos per week. I mean 1 to 2 tutorials per week, and that way we you can actually have you will immediately know when the videos are uploaded. Okay.